So I'm going to talk again pretty briefly this time, and then we'll launch into an actual demonstration of what's going on. But just to remind everyone, we're going to need some Java, and we've already got Skyline, and you'll need to make sure you've got that Walnut executable and that it launches correctly. Okay. Cool. So while we're doing that, and if you need to install anything, we can talk for a bit. So one of the questions that was brought up quite a bit this morning was, what happens if you don't have a full Spectrum library? Or how do you know how good your Spectrum library actually is, or the one that you downloaded from the web? And so sometimes you need to detect peptides that you can't find in a Spectrum library, or that someone else hasn't already collected data for. And so that's kind of the theme of what we're trying to do here. And so sometimes, basically, you just need to make detection straight from a FASTA, or straight from genomic sequence. And for example, splice variants might be one, or splice sites if you wanted to measure peptides that span splicing domains. That might be an example. There are a bunch of other reasons why you might not actually have an MS2 already for your peptides of interest. Okay, so to do this, we have been working on and published last year a project called Pecan, which is peptide-centric analysis straight from FASTA databases. And so to understand how it works, I think it's pretty useful to understand how normal search engines kind of do their thing. So a normal search engine like Sequest or Mascot is going to take a pile of spectra that you acquired, of DDA spectra that you acquired, and then take a sequence database and then try to figure out what is the best peptide that matches to that spectrum. It'll line up them all, and it'll say the top match for this one spectrum is peptide X. And then you can compute a p-value or a q-value straight from that using a program like Percolator or Peptide Prophet or something like that. Okay, so peptide-centric analysis takes this sort of mantra and flips it on its head. Instead of having a list of spectra that you want to know what peptides are assigned to them, we're asking the question reverse. We've got a list of peptides, and we want to know what spectra are assigned to them. And this is kind of like a really subtle flip that appears like it's a nonsense flip. But let me explain to you kind of what I'm talking about. Here, we've got a peptide of interest that we're interested in going after. And this is, again, something that Skyline or OpenSwath or other sort of library search tools do. They have a peptide of interest, and then they look for a signature for that peptide of interest across all of retention time. They'll find a point that scores really well, and they'll say that's where the peptide lies. The big change here is that you're asking, again, a question, one per every peptide, and you actually get a 0 potentially. You know when you don't actually have this peptide in your DIA file. And that, I think, or at least it's below the measurable level of analysis. But the idea here is that you would score this particular peptide at that time point and, again, collect a p-value or a q-value. Okay. So just to kind of reiterate how that actually works, here I've taken a particular peptide, I've extracted out all the B and Y ions associated for this particular peptide across all of retention time here, and I've run a score, or a search engine score. In this case, this is actually just running Sequest, or the Sequest-like score, X-score, against each of these MS2 scans in the raw file at every given time point. And I'm looking for the point at which you get a nice spike in that signal. And at that spiking time point, hopefully you see fragment ions that are associated with that shape of the peptide. And that's how library searching works. And that's also how a database searching works using Pecan. Okay, so let's talk about how this is different from what we were doing just in this last session, where we were doing some DDA-based library searching using Skyline. Okay, so a Skyline library searching strategy is going to be on the order of 1,000 to 10,000 peptides, or maybe 100,000 if it's a really big library. We're going to know something about its fragmentation patterns. We're going to know something about the retention times, or the relative retention times, using an IRT standard. And those two values, the fact that we're searching a pretty small search space of expected peptides, and we know quite a bit about what those peptides look like, means that we can do pretty sensitive, fast detections of those peptides. However, as we alluded to earlier in the morning, library development is pretty time-consuming, and it's pretty hard as well. So not only do you have to be able to do like really good offline fractionation, like SCX or reverse phase or high pH reverse phase, that you also have to potentially be able to do both of those and a bunch of DDA and spend a lot of time, maybe like a week's worth of data acquisition, just to get a good database library. Furthermore, it's pretty hard to develop this in an extensible way. So if you wanted to generate a library that contained a bunch of PTMs all of a sudden, or sequence variants or something like that, again, all of these libraries, you need to be able to have seen them before. And so if someone else hasn't detected your sequence variant or detected your PTM, then we don't really have a good representation of it. Database searching is disadvantageous in that instead of talking about searching a couple thousand or 10,000 or 100,000 spectra, we're talking about searching on the order of millions of peptides or tens of millions of peptides. That said, there are some, nice advantages. So that just looking for that many things actually makes it much harder for us to find them due to false discovery rate correction. It also makes it quite slow. But we do get the advantage of being able to find some of these peptides that span splicing junctions, or things that are otherwise hard to see, or are in a sample that no one else has considered before trying to do analysis. Say you wanted to do some proteomics of like honeybees or something unusual. This would be a mechanism to be able to do that without having to generate a robust library. Okay, so we mentioned a little bit about gas phase fractionation, and that's this idea of doing these multiple acquisitions here. What we find out is that while Pecan actually doesn't do that great at searching these wide window data sets, it does quite well at searching narrow window data sets. And think about what this means. So for example, in this situation, we've got 24 MZ wide windows up at the top. That's pretty wide. A search engine like Sequest is not really designed to search with a precursor isolation window of 24 MZ wide windows. But as you cut that down to 12 or to 6 or to 4 or to 2 MZ wide windows, once you start looking at 2 MZ wide windows, that's in the range that Sequest was designed to work in, because that program was designed to work for triple quads and for ion traps. And that's the mass resolution that those instruments have, right? So if we could figure out a way to like narrow this down even further, we would be able to do quite well with a situation like this. And so just to give you an idea as to what we're looking at, if you were to collect a DIA with Pecan looking at just the number of peptides, so this first circle here, that's using one gas phase fraction. That's as if you were searching with a very wide window, or a 20 MZ wide window, or 24 MZ wide window. If you were to use 2 gas phase fractions, you see a lot more. You recover all the peptides you found in a single gas phase fraction, but you see a lot more peptides. And if you use 4 gas phase fractions, that's divvying up the mass window into 4 different raw files, you actually see a lot more there too. On the other hand, with DDA actually doesn't benefit from this property of narrowing down the precursor isolation window set, right? Because it's really just the idea, I mean, basically the only thing that you get is more times of trying to detect peptides, that's it. It's like a bunch more replicates, and that's the only advantage. So the difference between 1 gas phase fraction with DDA versus 2 versus 4 doesn't really improve at all. And so if you look at the number of peptides in the 4 gas phase fractionation samples, you can do better with pecan than you do with DDA. That's sort of like the take-home message here. And the same thing works at the protein level. We don't have any missing proteins. As you narrow down your precursor isolation window and collect more fractions, we don't see fewer proteins. We only see more proteins. Like, we don't miss things. And that's, I think, very heartening. Whereas with DDA, again, you run the risk of just not happening to sample it in that specific run. Okay? Okay. So we've been working on, pecan was kind of like a preliminary product or preliminary program that we were developing and researching about. We've developed kind of like this usable framework that's in this Java program called Walnut that basically implements the pecan algorithm. Walnut is sort of like Walnut is like a pecan, but like maybe a little bit more wrinkly and somewhat more bitter. That's kind of like the difference between Sonia and I as well. So it's a pretty good representation of us in a nutshell. Yeah. So what's walnut? What? I'm definitely the walnut. Okay, so what Walnut is designed to do is to use the pecan algorithm, but be something that you can run on your desktop computer. So it's optimized to work as a multi-core search engine in the same sort of way that Sequest is designed to work as a multi-core search engine. And it's reasonably fast for this type of data. It's still a bit slower than Sequest because you're trying to do more with it, but the idea is pretty similar. Okay, so the idea here is you've got like a list of parameters that you want to enter in, and again, these are like normal search engine parameters, and you've got a way to add MZML files, so these are raw files, and then a way to save blibs so that you can visualize the data that you've generated in Skyline. Through the sort of library browser, and you can actually import your raw files on top of that library browser and actually extract out the particular peaks that were picked. And we're going to go through an example in which we're going to do that. Okay, so Walnut options. Walnut is basically like any normal database search engine. You've got a bunch of parameters in terms of what database you're looking at. You've got a background and a target. What this means is your background should be like a proteome. So if you're interested in human proteins, or if you've got a human protein sample, you might put in the human UniProt database. But your target could be anything that you are interested in measuring. And typically, it's like a subset of that database. So for example, the demonstration we're going to do here is we're going to extract out only peptides that are associated with the mTOR pathway. And that's it. And so basically you would enter in two databases here. One is the 9606, that's a taxonomy for Homo sapiens, and a target database that is just UniProt-mTOR, which only contains proteins that had a keyword associated with mTOR in them. Okay, so that can kind of make things a bit easier. You have acquisition settings. So you've got overlapping DIA versus non-overlapping DIA. And that's based on what we were talking about before. And if you have like if you're using a SciEx instrument, you might need to indicate what the precursor isolation window width was. Okay, so finally, you're going to have typical normal database search engine parameters. So things like what enzyme you used. Did you use fixed modifications of cysteine? What are your precursor and fragment mass tolerances? And how many miscleavages and what charge states you're willing to consider. Those are like normal questions that you're used to answering if you're using Mascot or Sequest. Okay, and so with that, we're just going to run through a demonstration of how to use this, again, using this mTOR example. Okay, so I'm going to go back to this page. Hopefully, if you needed to install Java, you've already installed Java. Hopefully, you should just be able to double-click on Walnut executable and launch it. All right, let's get started and start using this program. So again, you're going to be able to take this home and put it on your machines and start using it to your heart's content. So I'm just going to start filling in some of those slots. So we're going to set the background proteome, and I'm going to hit Edit here. And in this directory, there's going to be this 9606 FASTA, and I'm going to hit Open. Okay, so that's going to fill in for both the target and the background, actually, because we've queued it up once. So we're actually, because we don't want to search against the entire, all right, because we don't want to search against the entire human uniprot FASTA database, we're actually going to edit the second one, the target. And we're going to change that to this selected version, this uniprot mTOR database. This contains about 150 proteins in it that are, again, targeted towards mTOR pathways. Okay.
This targeted database, it should be a part of the background, or?
It should be a part of the background.
Should be.
Yes. Yeah, it should be a subset of the background. It just is an advantage sometimes to search a targeted database because, again, we're asking questions based on the number of peptides, right? So if we're asking for 1,000,000 peptides in the human proteome or 2,000,000 peptides in the human proteome, that's a lot of questions. But if we're asking for maybe 1,000 peptides out of the mTOR list of peptides, then that's not so bad. That's in a measurable range. Okay, so realistically, all of these other parameters, so we're going to do normal target decoy analysis, we're going to do just a and we're just going to add these MZML files. So there's 2 MZML files here, right? Okay, so I'm going to open these files. I actually pre-analyzed these for you because it takes like a little bit of time to do this analysis. This search on like a normal laptop would take around 15 minutes, and I just don't want to spend the 15 minutes. So we're going to go straight like this. So this has analyzed these 2 raw files. It's of the I don't know, couple thousand peptides that were in these FASTA databases, it's detected around 600, 700 files. So then we're going to click the Save blib option. And in this directory, I'm just going to make an mTOR blib. And so what it's doing, you can see this section down here scrolling away, this section right here. It's actually taking all of the peptides that were found in both of these files and then collecting them together into one kind of, or all of the peptides that it had information about in those files, collecting them together into one analysis and running a global percolator analysis across all of the files simultaneously. And so the idea here, what it's doing is it's we're trying to do the false discovery analysis all at once. Is that not good?
Oh, my computer's just dead.
Oh, okay.
So
Okay, cool. So it's running percolator across everything, trying to identify all of the peptides that are possible in the entire experiment in both files simultaneously. And then what it's going to do is, okay, it says, I've got X peptides that I've found. Now I'm going to go try to quantitatively extract these out of the raw files and decide what are good peak boundaries, for those different peptides in those different files. And if I don't find it in one sample or another, it's trying to extract out, kind of like figure out what is the best retention time point for that by doing a big retention time alignment between the two different raw file sets. So that's sort of what it's doing here in the background while it's thinking about this. Do you guys have questions about this or peptide-centric analysis in general while we're letting it process? It's doing a bunch of percolator analysis and then doing a bunch of extraction. What we're going to do is we're going to take the blib library that it generates. The blib will contain the retention times that we found those peptides in. It'll contain information about the integration boundaries and that kind of thing. And then we're going to load all of that stuff into Skyline directly. So we should be getting on our way. Is this working for those of you that are doing it? Okay, cool. So what it's doing at this step, for example, is just doing all of those integrations and figuring out what's what. So if I look at this directory here, or I guess when we finish running through this, we're going to end up with a blib, and we're also going to end up with what is called an integration file. And the integration file is going to give us a list of all of the boundaries that were found. And so in here, if I sort on, I guess, date modified, it's got this mtor blib that we created, and it's also got this mtor blib.integration. And that file is what we're going to use for kind of the further analysis that we're going to do. So once I've got this going, I'm just going to run Skyline, and I'm just going to make a blank document. I'm going to set the settings to default again, and not save it, no. And then we're going to go through and do like a bunch of these settings again. Are you guys at a reasonable stage here while this is, it can still be running in the back. And Pecan has already kind of figured out what peptides we want to look for. Okay, so I'm just going to hit OK at that point. And then I'm going to go to Settings, and then go to Transition Settings. And we're going to go through these next. So starting from the very beginning, we're going to check the prediction. We're going to make sure that we've got monoisotopic, monoisotopic for both the precursor and the product ions. And then for filter, we're going to make it so that the precursor charges are, say, we said 2 and 3, right? Because we were looking for peptides that were 2 and 3. And we're going to do ion charges of 1 and 2. So we're going to extract out +2 fragment ions too, if that's appropriate. And for the ion types, we only kind of did the analysis on the Y ions. We're also going to include precursors because I think it's useful to be able to see the precursors too. So Y, P is a good section for that field. And just like before, we're going to go from ion 3 to the last ion. So this time it's last ion, not last ion minus 1. So otherwise, everything else should be pretty much the same. So if I go to the library, this ion match tolerance is way too low. Since we're trying for about 10 ppm, I'm going to set this to 0.005. Which is about 10 ppm for a fragment ion that's at 500 mZ. And instead of 3 product ions, we're going to select 5, just like last time. And then finally predict, from filtered product ions, we're only going to select them from the filtered product ions. Again, just like last time. 0052, the method match tolerance. Because again, we search for 10 ppm in both cases. So these MZMLs, the raw files originally were collected in Profile, but we are analyzing them in Centroid. Okay, so for MSMS filtering, we did DIA, right? Just like before. The fragment ions are centroided. And here's kind of a trick. Instead of setting up, I don't really want you to do that. It's trying to restart the computer because it's got updates. Okay, so for the isolation scheme, I'm going to set it to results only. So before, when we were setting up isolation schemes, we're actually pre-calculating them on the fly for that type of instrument and that acquisition parameters that we were going to do. You can also just extract them out of the raw files, and that's all that the results only option does, is it extracts out the windowing scheme from the raw files. So, and I'm only going to use scans within 2 minutes of the MSMS time, just sort of like how we were doing before. Okay. So that's good. All right, so now that we've got our Skyline document set up, we need to do 2 things. We need to queue up the FASTA file, and we need to queue up the library. So over in settings, in peptide settings, over in the digestion settings, we're going to add a background proteome. So we added the yeast one last time, but this time we're going to add a new one that's going to be the mTOR proteome. So we're going to add, and I'm just going to call this mTOR. And for the proteome file, I'm going to create a file. Again, just like before, I'll be terrible and save it again on the desktop. And then we're going to add that mTOR file in. So the reason why we're only adding the mTOR, we could add in all of the files, all of the human FASTA, but there's really not any point because we know that all the peptides in our blib file are going to be mTOR peptides because that's all we searched. So we might as well just limit it to the Uniprot mTOR FASTA, because it'll make this part quite a bit faster. Okay, so has everyone got this? Is anyone a little bit behind on that? Still entering in stuff? Okay, I'm going to hit OK here. All right, so that's good. And now I'm going to enter in the library itself. So over again in peptide settings, there's this library tab. And here's the yeast DDA library that we built before, but we're going to build a new library here. Actually, instead of building it, we're just going to add it directly because we've already got the library built. So we're going to edit list instead, edit list, and then add to the list. So I'm going to call this mTOR again, and the path that I'm going to browse to is the blib that we generated. There should only be one blib in that section. And then I'm going to hit OK, and then OK, and then OK. And that's it. So we've loaded our mTOR FASTA, and we've loaded up our blib library file. Is anyone else still waiting on that? Okay, cool. Let's take a look at what the library file looks like. So I'm going to go to the spectral libraries in view. And if I select this down, there should be my mTOR list. So some peptides are going to be kind of like not great, like this one, for example, that only has 2 fragment ions in it. But a bunch of these are going to have, several Y-ion fragments that are reasonably associated with those peptides. So I'm going to, once again, just like before, we're going to click on associate proteins because we want to link all these peptides up to proteins. Sorry, guys.